Hello, this is my video report for Lab 1. So the purpose of this experiment is to observe the interactions of charged pieces of clear tape and determine how much excess charge is on one piece of tape. The results that we found was that the charge on the tape from the observed model was around 1.587 times 10 to the negative 8 coulombs, and from the computational model it was calculated to be 1.93 times 10 to the negative 9 coulombs. The number of electrons lost by each tape was found to be 9.92 times 10 to the 10 electrons. Some of the fundamental physical principles involved in this experiment is Newton's second law, which shows that the acceleration of an object is directly related to the net force. It's also known as the equation for F equals ma. And for Coulomb's law, it helps calculate the amount of force between two electrically charged particles, which can either be attractive or repulsive. This is our experimental setup for the observed model. Here are the initial conditions listed. The system is tape B and the surroundings is tape A and everything else. Before starting the experiment, we had to determine whether the charge of the tape was positive or negative. We did this by seeing how the charged plastic pen that was rubbed against wool interacted with the charged tape. We saw that the tape attracted to the plastic pen, and because the pen is negatively charged, the charge of the tape must be positive. We saw that the distance between the two positively charged tapes A and B repelled, which makes sense because the charges are both positive, and the distance from its original position of tape B was around 0.034 meters. Now here are our calculations. The force of gravity was calculated to be around 0.001962 newtons, and that was by using Newton's second law. And because the tape is stationary and not moving, we know that the net force acting on the tape has to be zero. And this means that the magnitudes of the force of gravity and the electric force must be equal. Knowing that, we used Coulomb's law to find the charge, and we estimate the charge to be about 1.587 times 10 to the negative 8 coulombs. As for the electrons lost, we just divided the charge of the tape by the charge of an electron and calculated it to be 9.92 times 10 to the 10 electrons. In the computational model, I treated the pieces of tape as point charges. The initial conditions were set the same as the observed model with the same values of tape mass, length, and width, and included the distance between the charged tapes. I also set the constants like K and G for calculating the electric force and gravitational force. In the code, I have calculated the gravitational force and have a function from lab 0 for the electric field. It was found that the magnitude of the electric force was 2.90115 times 10 to the negative 5, and the magnitude of the gravitational force is 1.962 times 10 to the negative 4. Based on the magnitude found for the electric force, the charge of the tape can be found using Coulomb's law, which is the same method as we use in the observed model, and it was determined to be around 1.93038 times 10 to the negative 9 coulombs. Some similarities and differences between the two models is that both charges of the models were calculated in the same way using the equation, and both were calculated to be very small. However, the charges of the tapes are pretty different with each model. The observed charge is greater by a whole magnitude compared to what was calculated in the computational model. And the discrepancy between the two models could be due to the assumptions made in our computational model. In our computational model, we neglected air resistance and friction, and tape was represented by a single point charge. Assumptions in the observed model was that each U tape made had the same amount of charge, where the charge was evenly distributed along the tape's length. Some possible sources of error could include the loss of charge when handling the tape. Sometimes we would handle the tape too much and it would actually lose its charge. And the mass of the tape was calculated, not measured. We also didn't consider other forces in the surroundings. And all of these factors could contribute to the inaccuracy of our results and our calculations. What if electrons had a positive charge and protons had negative charge? What would change about the observations you made with your tapes and other charged objects? The observations wouldn't change. Instead, there'd be a loss of protons instead of electrons, but the rules of attraction and repulsion still apply. For instance, opposites still attract and like charges still repel. Why is it important to handle the charged objects as little as possible? What happens when the charged tapes come into contact with your hands or other objects? So it's important to handle the charged objects as little as possible because touching it too much can lead to the loss of charge of the tape, as I said in the previous slide with the errors. And when it comes into contact with your hands or other objects, it can redistribute the charge to that new surface and make the tape neutral.